Okay, good morning, everybody. Thank you for coming to this last day of our visualizing ceramics, and structures tools workshop through the American Ceramic Society. It's been a great couple days so far. We've done a pretty good job of introducing the basics of reef refinement. Now, I'm not naive enough to say that in 2 days you're going to be pros at it, because realistically, when you learn this, you typically go for a week-long 9 to 5 boot camp. But I hope that I've given you enough of the tools to feel like empowered to get started and try it on your own. In fact, I've had 2 people so far from the class try it out and run into bumps in the road and get stuck and then contact me. And it was totally great. We hopped on a Zoom call and we were able to share screens and say, this is what's going on there. It was a pretty easy fix. So I'm anticipating that when you all try this out, that you might have a similar experience, and do feel free to reach out, because we're not gonna be able to spend more time on reef refinement today as much as I would like to, because I want to talk more about how to use Vesta and more about how to turn our refinements into beautiful figures. So we're gonna spend most of our time today talking about those 2 things. So I think we'll pick up where we left off, which is using Vesta. And I'm seeing some notes, that people try it out later. Feel free to reach out. Like I said, you guys paid for this, and so going forward, I'm at your disposal. I'm going to go through a couple of the common ceramic structures. After all, this is the American Ceramic Society. Let's go through some of the basic structures, and I'm going to show them in Vesta and show you how I would maximize how to visualize those structures using the tools that Vesta provides. So with that said, go ahead and share the screen, and we'll get started. Okay, so I'm going to jump over to Vesta, which again runs out of just a folder. So I've got it here on my desktop. I'll come down and open Vesta up. Okay. Now the structures that you're going to see today that I will be covering, get that out of the way, the Zoom stuff out of the way. You can download pretty much all of these from the crystallographic open database, but I've also provided them for you. So if you come over here to the GitHub page, I've added a few new files. So if you only saved this once by downloading everything one time, you might want to download it this last time. I don't think I'll make new changes to it after this. But you'll know if I do, because it will say that it's been updated. For example, I just added some things 2 minutes ago, right? But if you download the whole thing now, you'll notice that there's a couple extra folders. In the past, we had the felt refinement slides, and then I had some structures, basically. Now I'm going to have, or sorry, I had refinement examples. Now I've added 2 additional folders, one with structure examples. These are going to be common ceramic structures, and the other with plotting examples, which is going to have some information for plotting things. So in this structure examples folder, you have a whole bunch of interesting ceramic structures. And we'll just look through some of these. We probably don't have time to do all of them, but we'll look through a few of these and talk about how Vesta could be used to visualize these things. So you have access to those. Or you could go to the crystallographic open database and you could download them and practice trying to download them. And that's okay too. So I'm going to hop over to my structure examples, and let's just open a few of these up. For example, we talked about the apatite structure. I haven't associated with my Vesta yet, so let me, should probably just do that today, but for now, I'll just drag it in. So I think last time we talked about the apatite crystal structure. So fluorapatite, the same stuff that your teeth are made up of, right? These are naturally hydroxyapatite. And if you're using fluoride toothpaste, then you're actually introducing fluorine, which is doing an ion exchange for the oxygen atom, and that strengthens the structure. But your bones are made of this. Like, this is a very important ceramic biomineral. And when you load the structure, this might be the first thing that you see. There's a couple things to be aware of in Vesta, tools that you can use. First off, you definitely want to use a mouse. You can use a trackpad, but I think a mouse is going to be more easy to use with this. And in this space where you see the image, you can actually click it and drag it to rotate this image. It's pretty intuitive, right? When you rotate left to right, you're going to rotate in the plane, whatever it showed up in. If I rotate top to bottom, I'm going to rotate in that plane. You can rotate off axis. You can sort of rotate it in little circles, and you see it slightly does macro level rotation. So the whole thing is sort of spinning. So it's a pretty slick tool to show things. You can see that, if you're rotating it, you don't get it quite lined up how you liked it when it first started, not a problem. You can come back up here, and along the top, you have the ability to select different view axes. Like, I can look down the A axis by clicking that A button, or I can look down the B axis. Or in this case, the most relevant axis is to look down the C axis. That's usually how we think of the apatite crystal structure, okay? You'll notice that there are these, you can click on the atoms. actually, it would help if there's these tooltips over here. The gray arrow is the rotate arrow, and then this one right here is the select arrow. So by doing that select arrow, now I can select this ion, or I can select an individual atom. The atoms will turn yellow when you select them. The polyhedra, the blue's not changing very much, but they do change color. We'll show you with some other ones. And when you do that, if you notice here at the bottom, there's this information that pops up, right? When I grab like this red atom, red is by default always the color they use for oxygen, right? It'll pull up information on things. So let's grab this polyhedra. And when I do it, you see that right away it tells me what this polyhedron is made of. It says, okay, this polyhedron is silicon bonded to silicon, right? And then is made up of Si1 located at these position, and it's bonded to these oxygen. So there's a silicon in the middle, and it has these 4 oxygen on the tetrahedra. And it tells you exactly which ones, and it tells you their exact coordinates, which is kind of nice, right? But furthermore, it tells you down here at the bottom, it shows you the bond distances, right, between those different things. In this case, it's not a perfect tetrahedra where every bond distance is the exact same. One of those bond distances is slightly shorter than the other 3, which are pretty much the same. So this is technically a slightly distorted polyhedra. If you think of like a sort of the pyramid shape, it's like it's a little bit shorter on the top. It's like a squatty pyramid, just slightly, okay? So it gives you average bond lengths. It gives you the volume of that. Like all this really cool stuff is just default when you select it, which is cool. Furthermore, right now you can see that this is actually showing one unit cell where the unit cell is bounded by these bounding boxes of the unit cell, but there's clearly, you know, another unit cell here, another one there. So this is actually a 3 by 3 matrix of unit cells. And since we can go back to rotate and see that it's only one unit cell in the C direction, right? That this is a 3 by 3. So this is 9 unit cells. Okay. So it's helpful to be able to visualize things. You can actually delete things away. So let's say I look back on the C-axis and I didn't want to show all 9 unit cells. I can actually highlight all of these atoms that are not included in that unit cell, and I can hit delete and they will disappear from the image, right? I can do the same thing over here. Take those, you can hit delete. You can do it one at a time if you want. Oops. Clicked off screen for a second there. Let's try that again. Right, you can delete these out until you get just a single unit cell. And when you want them to come back, you just hit the escape button and they'll appear again. So pretty slick tools to be able to show these. There's different ways of visualizing the atoms. Like maybe you don't want that it's showing you the entire polyhedra of the silica bonded like that. Well, you can just do individual atoms, right? You can come over here and you can do space filling. The problem with space filling is that in this picture, I just told you that the red atoms are oxygen. And if you guys have worked with crystal structures for a while, something should be a red flag here. It's showing you all the cations are larger than the anions. That's because it's not using the correct ionic radii by default. If you come up here to your edit your data and you go to the structure, if we go to the structure parameters where the actual ions got inserted, yeah, see, look, these were put in with 0 charge. So these are just put in as atoms, not as ions. And so it's not using the correct ionic radii because they were not provided. So you do have to be a little bit careful. And even if you set it, I would not necessarily trust that it's plotting things accurately with the space filling model. Instead, the space filling model simply says, if you allow things to expand equivalently, they'll stop when they touch each other. A much better way to do this would be either ball and stick, right, which shows you where bonds are at, or polyhedra. You could do other ones, like there's these wireframes. These are common in organic chemistry, but I don't see them as often in inorganic chemistry. I think polyhedra is by far the best tool here to use, but you have options. Now, I think we left off last time talking about that bonds were present. So we can modify those bonds. Right now, it's only showing you the connectivity of these silicate groups, but maybe you want to show other bonding that could be present. Well, you can do that, right? You come over here to your edit and we go to bonds, and you can add as many bonds to anything you want in whatever bounds you want, even unphysical ones like we showed you last time. But in this case, let's do another one. Let's add a new bond. And this time we want to bond something like, you know, let's see if our lithium or lanthanum, excuse me, is bonded to oxygen. So the default setting is it's going to look between 0 and 1.6 length. We're not going to find anything that close. That's too short of a bond. If you increase this to 3, we might find something. Yeah, okay. So now you have another way of viewing the structure. If we go back to our rotate tool, now you can see that we have taken these lanthanum and created polyhedra out of their bonds with oxygen. And if you were to, zoom in on that, it actually is able to capture them and it'll tell you something about them, what this supposed structure is, whether it's, even real or not. Let's just grab one of those. So right here, it's saying, okay, in that polyhedra, you've got lanthanum bonded to 1, 2, 3, 4, 5, 6, 7. So that's an unusual coordination number to have 7 bonds coordinating a cation. But again, just because you can visualize this doesn't necessarily mean that those are real bonds or that it's the best way to represent a structure, but it does give you the option to explore these things. Clearly what we're seeing here is that there's 2 different cation sites. Let me get rid of the bonds for a moment and show you what I'm talking about. Go back to our bonds, edit bonds. I'm going to delete that one out. There's 2 different sites. I'm going to zoom in. So you have this zoom in button on the top. You can zoom in. And you can also move things, like scale them up and down. Like here, I'm scaling this up so you can see that just first unit cell. What I wanted to point out is there's different cation sites. Like this guy right here is one cation site, and that's a different site than this one. And what we were showing you is that these ones, let me unclick those. I'm going to hold down the shift button to capture multiple atoms at once. All of these ones, excuse me, there we go. All of these ones were the bonds that it was just capturing because they are closer to oxygens than these ones, which were not as close. Okay. So that's a few things we can say about generally in the apatite structure. When we think about the apatite structure, it's often thought of in terms of an oxygen ion conductor, and you get these pathways that travel right through it. That is easier to see when you visualize it with just these silicate groups bonded without the other bonds, which makes it a little bit harder to see. Let's say that you didn't like the colors here, like you thought that the calcium, which is this sort of metallic blue, is too close in color to the silicate groups. You can change all of that, right? All of your aspects of the colors can be changed. If you come over here to properties, the individual atoms, right now, if I select the calcium, which has that sort of metallic blue, if that was too hard to see, that it was too similar, well, it's nice that you can just select a different color. You can actually provide the RGB values or just select from this, preset, different ones. Maybe you think purple would be a better choice, for example, and you can, release that. You can actually edit all sorts of different things. Like if we come back over here to properties, you can actually not just modify individual atoms, but you can make bonds have a certain color or gradient in colors. Do you want it to be like a bicolor cylinder or a gradient between the two? The polyhedra, do you want them to show the atoms on the corners? Right there, it's showing them on the corners. You can make them show on the corners and you can see the bonds inside that are present. You can put just the atom in the middle, but don't show the bonds or the atoms on the corners, or the default value in this was just to put the triangles, or you could show them like this, right? You have all sorts of options for how you want your polyhedra to be represented. So you can sort of choose the one that makes it easiest to see what's going on for your individual scenario. So why did it show us a 3x3 matrix? That's because what I opened was a .vesta file. A .vesta file means something that has been saved in Vesta before. If you were to open this just as a sieve card, let's look at the difference. So if I come back to my folder, here's just the apatite sieve card. If I drop that in, it's going to look different, right? Because you just provided a sieve card, what it's going to do is by default look for bonds. It's only going to show one unit cell. And so this is not the ideal way to show that structure. This is a much more useful way because it shows the channels whereby you get oxygen ion conduction, for example. But you could go from this to that pretty easily. Let's do it real quick. So first off, let's remove the bonds, which are going to be distracting. Because again, if I go to polyhedral filling, it's hard to see the rotations that we care about in this way. So instead, let's go back, let's look down the C-axis. Let's turn off some of the bonds. So just Control B is a shortcut to get to your bonds. I'm going to turn off my calcium oxide bonds and my lanthanum oxide bonds and just show the silicates. I happen to like it in this one when we turn off the atoms on the corners of the polyhedra for this particular structure because it's already kind of busy. And then the last thing is let's show multiple different unit cells. So down here at the bottom, there's this boundary. So we're going to go to boundaries and I'm going to say, give me all the unit cells going out 3 unit cells in the X direction, 3 in the Y, 3 in the Z direction. There we go. Now we've got that same structure that we had before. So very useful bit of software. If you're not going to be using this information on the bottom, you can minimize it and give you more space to actually see the structure if that's something that you'd prefer. But pretty great. Let's look at a few others. So I'm going to close these out. I think Control W closes them. Don't want to save. Don't want to save. Okay, let's look at a few others. How about these ones? These are a family of perovskite-like materials. These are in the layered perovskite family. Oh, let me see a few questions popping up. Okay, yeah, great. If you got questions, feel free to interrupt. I'm happy to sort of monitor those. And if I'm not seeing them, somebody can feel free to turn the mic on and just ask the question. But there's a lot of layered perovskite materials. This is one example of a layered perovskite. It's the aurelius phase, a pretty common ceramic. It can be thought of as an inner growth between two different types of layers. You have your fluorite block. This looks like fluorite there in the middle. And then you have your perovskite block. And so it's these inner growth between those different phases. So you can see this if you kind of rotate them. You might find the one that can most easily show up, but this is pretty clearly a perovskite block, and there's your fluorite. Again, the best way to show this is with that polyhedral view. I think looking straight down one of the axes, pick one where you can see the layered nature, like A, for example. If you did just ball and stick, it's going to be maybe okay. Space filling is going to be really hard to see what's going on here, but maybe that's also okay. Again, it's getting the sizes all wrong. Oxygens are way bigger than whatever this purple, I think it's bismuth. That's just wrong. So you'll want to be careful. I do think polyhedral is probably the best way to go on this. In this case, it's not showing the bonds between your oxygen and your bismuth, even though they're close enough that they're certainly bonded. It's just easier to see the structure when you've chosen certain polyhedra to be turned on. And honestly, that's how most ceramic structures are thought of, is in terms of connectivity of polyhedra. Let's say that you did this and you were ready to export this image. You liked it so much, you're going to use it in a paper. You can come up here to your file and you have this export. You have two options. You can export the raster image, which will be basically a bitmap file that this generates, or you can do the vector image, which is something that you could open in like Adobe Illustrator. Unfortunately, my experience, I've wanted to use the vector image, but my experience has been that it's not very good. We can try it again and see if they've updated it. But see how like these polyhedra have some partial transparency, which again is a property that you can update over here in our polyhedra. You can change the degree of opacity. Right now it's at 204. So let's make that like 225. And you see when we apply that, it's the opacity has changed there. Let's try it one more time. Let's go the other way. If we come back here, we go to our polyhedra. Let's change this down to like 15. They should be like barely visible now, right? The opacity is a tunable parameter. What I've found is that when you export this as a vector image, those things get lost. In other words, there's some visualization rendering software happening in Vesta, which is not preserved in like an EPS file. But let's give it a shot and try it real quick. So in that same folder, we should now have a EPS folder for our Arvelius phase. Let me make sure that's saved to the spot I thought it saved to. Oh, it's outputting it still. Okay. This can get kind of slow. If you have a really big structure, like here we have, hundreds of atoms, probably, maybe around 100 atoms. And because we're generating as an output a vector image, every single atom is getting generated as an object in that vector file. So it took, this is not like a chintzy laptop, it took, I don't know, 20 or 30 seconds. So realize if you do even bigger, it can start to go really slow to not just output, but to render in real time. Where did that save to? I think it would put it here. Okay, here it is. Here's our EPS file. So let's open this in Adobe Illustrator and see. I'll give you a feel for what a vector image output is going to be. We'll give that just a minute to do that. But if you didn't want to do that, you can also export it as a raster image. One thing that I like about this one, okay, so it gives you options. There's TIFF file, bitmap, JPEG, whatever you want. If you want every single pixel, the default is TIFF. If you don't mind some compression, do a ping, for example. I think it should give you, yeah, right here, it gives you the option to scale it. Right now, it's going to use the exact pixel resolution that I have on my screen, but you could increase it. Maybe you want like a really big image because you're going to print a poster and you don't want grainy images. You can also make the background transparent since this is a ping, and you can output this. Again, it might take just a moment for this to run. Let's meanwhile hop over to our Illustrator. So first thing it says is like, hey, I don't have some of the fonts that you were using. So you say, I don't care. We can change the fonts later. No big deal. We'll skip that. But again, take a look at this. Like it's It's really a far cry from what you were probably expecting. My experience with the rendering as an EPS has just not been very good. um, you can see where what it's trying to do. Like every one of these atoms is like a complicated vector image. It's just not doing what I want it to do. So I almost never do vector outputs. And I instead try and just get it to look really good in Vesta, and then I export a raster image. But maybe you guys will have better luck with that. Okay, so it says, great, I was able to output that. So let's jump over to wherever that was output. Where's our PNG file? Right here. And again, because I asked it to do transparent background, that's why you're seeing it with no background that's transparent, not white or black. It's just not there. But it's pretty okay. Like I accidentally had that atom highlighted, so it's showing up as yellow. That's the highlight color when you select an atom. But it's pretty slick. And because I did that with pretty high resolution, I can zoom pretty far in on this. So if you wanted to print this for a poster or something, you can do so. And because it's transparent, if your poster had some background image or a gradient in color or whatever else, you can do so. Where I've seen this used to really good effect is in table of content, graphics and things like that. You can show mechanistically what's going on. Maybe you have like a battery intercalation, problem you're working on. With the right sort of choice here, you can do a really good job of demonstrating this. And I think in a moment I can pull up an example of that. But those are two examples. Just be aware that if you increase the resolution, the size of these things, especially if you're not doing like a PNG, which is a compressed image format, if you did a TIFF, those can get really big. The memory can get really large. And like I said, if you add a lot of atoms, then the rendering can become slow. Let me hop over to the chat, see if there's any questions. Okay, yeah. So this person says when they're looking, they don't see an option to download the entire structure example folder from GitHub. Oh, that's an interesting question. I think what you could probably do is come back to the main ceramic page here. And from the ceramic, you should be able to download the code. I don't know if you can do it for just the structure examples. Yeah, I don't know if you can do that. Just download the whole thing is my recommendation. Or you could download individual files if you want. The best way to go is to learn how to use Git so that it updates these things automatically. For example, when I make a change to Git, like let me show you in real time what happens. Let's be brief about this. Let's say I'm updating the README file, which tells people how to use this repository, and I add an exclamation point. So I've technically made a change to the actual repository. Check it out. Because I'm using Git, in a moment, my Git thing here is going to say, hey, there's been a change. It takes a moment to sort of update. Did I actually save that? Sorry, 1 second to look. Like I add an exclamation point here. So then down here, how do I get it to pull? I have to tell it to, yeah, right here, fetch. Every so often it's going to check to see if there's any changes. It says, hey, I found some changes from the last time that you worked on this. And then it will automatically pull those files down to my computer. So now in my computer where I have that thing fold, inside that README file that I just worked on, technically now if we open this thing up, that exclamation point is there, right? So it Git is the way, there's a reason why computer programmers use Git to manage code because it's just seamless. It makes it super easy. So that's my recommendation for you there. Other questions. What size is that raster image export of Vesta and is it a TIFF? Oh yeah, I got that question. Okay, great. Let me keep going then. So let me point out just how slow this can get. Let me add some silly boundaries. Let's say that I wanted to plot like, 10 by 10 by, we can go negative direction, by the way, by -10, right? So this is now going to be a really big representation. There's gonna be a lot of atoms. And my computer, it's not like terrible, but still, like if I try and rotate this, here I'm actually dragging it with my mouse and you're not even seeing anything happen because it's trying to render many, many, many atoms. In fact, maybe we can get a quick count of atoms. If I go to my select tool and I highlight these, it's taking forever to render. It'll actually tell you how many atoms are there, which is kind of a cool tool in and of itself to be able to count and report that. It should show up if you give it a moment. It's thinking really hard about this. At the bottom, it should show you like the total number of atoms that you've collected. Oh, this might be like a losing proposition. It's just too slow. But the point is, I hope taken that if you make it too big, you might run into some unpleasant, speed problems with this. So choose wisely based off of your system. Got it for the main 60 to 63,000 atoms, bonkers. So yeah, see, it's still thinking. So I'm just gonna actually, you can actually control alternate delete and actually tell it to just stop, like kill the program, because the process is just gonna take a really long time if you want. So let's just kill it in task manager. We'll just end that task and then we can reopen it. It's not a big deal. Come back to our Vesta folder, open it in Vesta. Okay, and let's look at a few other structures. We won't spend all day doing this, but we'll show you some other ones that I think are useful. What about some classic structures like fluorite, right? So fluorite, very common structure, the fluorite structure. Again, you could show this with just atoms. We could turn off all the bonds. Let's just do ball and stick for a moment. That would be one common way. Like if you see behind me in my graph, I've got these structures up my wall. That's a common way that we represent things just with ball and stick. But I think polyhedral is the way to go because it clearly shows you that that the coordination number for the cations is 8. So they have cubic surroundings, but there are big chunks of this structure which are unoccupied, which are empty space, which is why these things are not like high packing structures, right? They're not nearly the high densities of, say, metals because you have big blocks of this which are unoccupied space. Okay. It also has a ratio of 1 to 2, 1 cation for every 2 anions, right? Therefore, we know that there are twice as many anions, these gray ones, as there are the metallic blue ones, which are the cations, which again gives rise to why there's missing holes where the cations would occupy if it was a one-to-one structure. Okay, what if you wanted in this structure, so let me look along just one of the axes. You can look along anyone you want. By the way, if you want to do like a very specific rotation, let's say that I'm looking along the a-axis and I want to look exactly like 45 degrees between the A and the C axes, I can do that using, I tell it the step size and then I can click it right there. And now I'm looking exactly at 45 degrees along that new direction. And then I could do another rotation, 45 degrees down. And now I'm looking exactly along the 111 direction, right? Did it get exactly? I think it's pretty close. Anyway, so there are tools to do specific rotations. Again, if it's too zoomed in, you can adjust your zoom, get it however you want. Let's say that for whatever reason, your structure, you know that there's a variation of this fluorite structure. Like maybe it's been doped with something, right? Maybe you've doped it with some other divalent cation like magnesium, right? So you could come over here and you could take an existing structure from a sieve card or a Vesta file. You could open that up and you could modify it, right? You could change the unit cell, make it 15, right? Some crazy number, like that's way too big, right? But it'll still do it. Notice that it turned off all of the bonds because the way that it was calculating bonds was by looking for a number between 0 and 3 angstroms. And so now those bonds, these atoms are way further apart. It doesn't mean that this is a real structure. This is now a hypothetical nonsense structure because we made it so big, but it will still do it, right? Just it will do what you tell it to do, even if it's nonsense. So let's go back and you can undo. So we'll go back and look back at our structure again. But let's say that you did want to add magnesium. You could come up to edit, you could edit data, structure parameters. And here right now we have calcium fully occupying the 000 site. Well, we could add another atom, right? Instead of calcium, you could say magnesium, for example. If it's got the same charge, name it something like magnesium 1. Maybe it's got the same charge and adjust its occupancy. Maybe it's like 25% of the time it occupies that site, okay? And then over here, we need to adjust this occupancy, make it 0.75, right? 75% of the time it's occupied. And now you would have a modified version of your structure. Again, if we turn off our polyhedra and do ball and stick, you can see that the way that they represent occupancy is as a sort of pie chart on the atoms, where if you click any one of these, it should tell you down here, that is the calcium on the calcium 1 site. I'm surprised that doesn't tell me that it's also magnesium. Yeah, it's not showing magnesium. I would have thought that it would. By the way, you can select individual bonds. Let me rotate it so I can just see one bond. And if I select it, it will give you information on that individual bond down here. Give it a moment to update. Try that one more time. It should. Maybe I need to grab the whole thing and it will give me several. Yeah, here's the individual bonds happening in it. Okay, so that's the fluorite structure, and we've showed you how to modify it. What if you wanted to show a plane in this structure, right? So you're back interested to showing this structure, but now you want to show a specific plane, like you want to see the 110 face, which should be like this face on the far right-hand side. Well, we can do that. We can go up to edit, and instead of modifying bonds, we're now going to modify either vectors, which would be, vectors on an individual atom or something, and planes. Let's do planes first. So if I want to show the 100 plane, I'm going to add a new plane. And by default, it is the 100 plane. But you also need to modify where it's showing up in terms of distance from the origin. Right now, by default, it's showing up 1 d spacing away from the origin, okay? So how is that? Are we actually seeing that? If we go back to our ball and stick model, let's rotate our structure. I'm going to zoom out just a smidge. And I'm going to rotate. So we're not seeing the unit cell boundaries. Let's turn those on. If you don't see your boundaries, that's a property that you can adjust, right? So right now okay, so for the unit cell, it's not showing the lines. Let's turn the lines on. And you can see that sure enough that pink plane is showing up along that side of the cube, okay? What if you didn't want it to be right there? What if you wanted it to be some other distance away? You can modify that. If you come over here to your lattice planes, you could show it half of a d spacing away, right? 0.5, and you could apply that just by stepping off it. And now it's showing up half the way through. Or maybe you want it to go right through the origin. I think you can do that too, and it'll show up right now going through the origin. Or if you want it like 3 interplanar spacings away, technically it'll do that. I'm gonna have to zoom out to see it. Oh, it's not showing it. Interesting. I would have thought it would show it. I guess it'll only show it if there's atoms there for it to show through, or or probably if it's within the bounds that you're exploring. Let's do this. Yeah, they're okay. When I go out 3, since I told it to go 3 away, then it'll show it. Interesting. So those bounds not only influence where atoms get plotted, but where your planes get plotted. Okay. And you can have multiples of these. Like if you want to show the 111 plane as well, you can do that. We'll do a new one. This time we want the 111 plane. And let's say you want it, again, however many d spacings away you want it. Let's just do 1 d spacing away. That's the most common way to treat it. Let's go back to this one and make this one only 1 d spacing away so that we can update our boundary and go back to 1 unit cell for clarity. And there you've got it. Now you've got that 111 plane. There's kind of a lot going on, so I'm going to reduce this, and I'm going to turn off our bonds for a moment. I'm just going to kill our bonds, just so it's easier to see these things. So yeah, you can see our 2 different planes, the 100 and the 111 plane are now both plotted. What if you wanted a bunch of the 111 planes? You want to see like the family of them because you're teaching a class on X-ray diffraction and you want to show them that it's the distance between those planes. Great, we can do that. Let's go back to our vector planes. Let's delete out the 111. Let's modify it. Let's turn it into a 111 plane. Oops. And let's make it 2 d spacings away. So now you've got the first one here, which was 1 d spacing away. We did another one that's 2 d spacings away. Let's do a third one. Let's add another 1 plane, which is 3 d spacings away. And now let's make this just a little bit bigger in terms of unit cells. We'll do 2 in each direction, so it's not too crazy big. But now you've got the tool to see where the family of planes is all completely symmetric. They all intersect the same types of atoms, right? Because of the symmetry of this crystal. But you can now see the d spacing between them. I'm going to rotate it a little bit until I see that we have now our d spacing right there, right? So really great for generating schematics for papers or for lessons or for whatever it is you're wanting to understand the crystal structure for. It's a great way to visualize it. Okay. Obviously, just like before, you can change the colors of things. Like if we go back up to our planes, I think we modified them in here. Yeah, here's our chance to change the colors. If you didn't like this pink color and that level of transparency, of course, you can change them to whatever you do like, right? And you can do it on a specific plane level, or you can do it for all of them. The shininess, the spectral nature, specular nature is all stuff that you can update. Now, you can and calculate the best plane. I've never used that tool. Oh, interesting. Please select 3 atoms before using this function. It'll actually find the plane that maybe that's a new function. I haven't seen that before. So let's try that out. Let's try selecting 3 atoms. So I'm going to delete out our planes for a moment. This is cool if they've added that. I don't think that used to be there. I'm just going to look at 1 unit cell so it's clear. Okay, let's say that I wanted it to capture, let me turn on rotate. I just want to capture these. Let's do like down the middle, like what should be the 110 plane. We're going to try and capture these guys. So let's turn on our selecting points, and it says to grab 3 atoms in that plane. So let's select like this one, that one, and that one. Let me make sure that I've still got those in the right plane. Yeah. So we've got three atoms. Let's see if it can find the right plane that encompasses those. Um, no, that's grayed out. Okay, right here. Oh yeah, and it does it. How cool is that? Way to go, Vesta. I didn't know they could do that. It's really cool. So if you had specific atoms that you are interested in, but you didn't know which plane, you didn't want to do the math to figure it out yourself, now you've got a way to do it. And that was an easy one, the 110 plane. But you can imagine there's lots of not easy atoms that you could pick. Let's try a harder one real quick since we've got it open. So I'm going to unselect it, and now I'm going to select three sort of oddballs.
Real quick, how did you get rid of the bonds again?
How do I get rid of the what now?
Bonds.
Oh, bonds. If you hit Control B, that's the shortcut, or you can come up here to edit and you go to bonds. You can just select it and delete it. Like if
Ah,
I, here it's adding them by default. Bond our calcium to our fluorine. Look out a distance of 3 angstroms. That's the typical value. Okay, now I've got those bonds. If you don't like those, you can just highlight this whole thing and hit delete.
okay. Thank you.
And then I'm probably more interested than you guys are at this point. I'll just do a quick example because I'm really curious if it can do this. Like, is there some goofy plane that captures these three? Like that is an unusual plane for sure. Let's see if it can find that weirdo plane. Yeah, the 251 plane. Super cool. Super, super cool. And it even knows that it's 3D spacings away. So that is a cool bit of software I didn't know they had in here. Very rad. Okay, but let's say that you are now interested in not just showing planes, and planes are interesting, but sometimes we want individual vectors on atoms. Maybe that represents like a displacement or a polarization or a magnetic moment or whatever else, right? So let's hop over to another structure, a spinel structure, since we're talking about magnetism maybe, and let's show you how you would put magnetic moments on these things, right? So spinel, let's pick like this guy right here. That's not a magnetic one, but whatever. Close this one. So now in the spinel structure, you guys might be familiar with the spinel crystal structure, that it is made up of a mixture of tetrahedral sites and octahedral sites. And I remember in grad school when I learned about this, they told me like it was actually one of the experts in this area, is a lady named Nicholas Spalding. She was teaching about the structure, and she's like, the octahedral sites are edge shared, right? So you've got these octahedra, um, these guys. Oh, why is that grabbing everybody? I don't want to grab everyone. By the way, you can hold down control on your mouse and scroll, and it should give you this option. Interesting, it's grabbing everything. That is unusual. I'm not quite sure what's doing that. Yeah, it's grabbing all the polyhedra. So they must have updated something in their selection tool, because it should be possible to select individual polyhedra, and I'm not sure why it's not doing that. So I can dig into that after this class and tell you what's going on. But in any case, I remember learning about this thinking like, I don't know if I see that because they said that they are edge shared and they were sort of like crisscross fries, like waffle fries cuts. And I'm looking at this thing like, I don't think I see that. But if you want to, you can just delete out the other ones. I think I've already done it for you here. So here I'm just showing you, um, oh, octahedral only. Let's take this structure and let's delete out the tetrahedral sites so that you can see this connectivity. So we're going to go over here. We're going to go to edit data, structure parameters. And we're just going to delete out the A site, which in this case is going to be our magnesium site. So when we delete it out, now what you're left with is a way of visualizing these. It might help if we show a couple more unit cells. So again, now you can see like, oh yeah, okay, these are edge shared clearly, and they are sort of like waffle cut fries shaped. So I think opening these structures up when you read about them in papers and they describe some aspect of the bonding or something, it's just way easier if you actually try and visualize the structure yourself. And don't be afraid to like delete atoms out. You can always add them back in later, and that's not a problem, so that you can visualize things. In any case, you got this structure that maybe you're happy with, like it's looking pretty good. You like that it's showing the octahedra and the tetrahedra and how they're all connected. But what you really want to show is another image where you show that there is a magnetic moment on the, let's say, the A site, and it is anti ferromagnetically aligned with the B site. So in that case, all of these bonds are going to be distracting. So we're going to want to turn our bonds off. So we'll come here, we'll delete these out. So now you just have the atoms. Um, let's turn our unit cell on by going to properties and turning on the unit cell. Just a single one's fine. Okay. Now what we want to show is that where the atoms are at, is where the magnetic moments are at. So we're going to go now to edit. We're going to add vectors. And you can do this for all sites or you can do it on individual atoms. So by default, it's going to do it on all sites. But if you want to select and put a bond on an individual atom, you can also do it. Let's do all sites first. On every one of our magnesium sites, we want to introduce a new vector. And we want it to be maybe pointing just straight up, 0, 0, 1. That's fine. You can change how long you want this thing to be. Like, here's the default settings. If I do nothing, this is the default setting. It's going to apply it to all of my magnesium sites. I'm not seeing anything. What did I do wrong? Bonds. Oh, not bonds, excuse me. Vectors. Ah, I see the problem. So you have to select where's the crystallographic site and what vector do you want on it, and you have to hit this set button. That's what I forgot to do. So by default, it's using really big values, right? Take a look, like those vectors are humongous. If I zoom way out, you can see how long each of those are. They're too big, right? So you can modify that. You come over here, go back to vectors, and when you modify the vector itself, let's go to edit that vector. The radius and the modulus. I think that the radius is like how wide that thing is. Let's make that a little smaller, like by half. And let's make the modulus, which is I think the length of it, cut that way down to like 3. Okay, that's still too big. So let's modify that and make the modulus like 1.5, half again. Maybe that's even still too big. Let's do it one more time. Let's go down to like 0.75. Yeah, maybe that's okay. So now when I zoom in on the structure, I'm able to see that all of those are anti-aligned, right? They're all anti-aligned, which is why, a lot of these materials are anti-ferromagnets, because you can see that there's the same number of these pointing up as there are down. If you extend the unit cell beyond just one unit cell, it might be easier to see that. Okay. So that would be an example of why you might want to choose to put an individual vector on one of these things, which is pretty slick. Let's see, we're at about half of our time. I don't want to spend all of our time talking about Vesta. Let me show you a few other things. I mentioned before some of these utilities, which are awesome. By far the most common one that I use is this powder diffraction pattern, where for this material, you can calculate it under whatever conditions you want. Like right now, the default is set for copper radiation, but you could put in values for cobalt or molybdenum or whatever values you want, and you can calculate the pattern, and it will actually show you what the expected diffraction pattern is, which is so cool. Again, it's assuming some level of like peak shape. It's assuming a peak shape, and I don't think it lets you alter the peak shape. Data range, Lorentz closure. No, it doesn't allow you to change the shape of the peak, just aspects related to like what's the ratio between K alpha 1, K alpha 2, that's right there. If there's a shift in the zero, like if your machine is slightly shifted, it allows you to adjust for things like that. But this is really great too. Here it shows you like a table of all those peaks that you see. Like for example, let's zoom out. This very first peak, which has both K alpha 1 and K alpha 2, it's happening around 19 degrees. You can come over here and it will tell you like, oh, that peak that you see at 19.08 and 19.12, that's coming from K alpha 1 and K alpha 2. Like it tells you that here's your lambda, that's 1 and 2, telling you that it's coming from those two different alpha 1 and alpha 2. And it shows you that's the 111 peak causing that. So in terms of diffraction analysis, you don't have to apply to Bragg's law. You should understand it, but this just makes it super easy to analyze what peaks are coming from what. Like if you had a textured material and you expected to only see like the OOC planes, right? Well, then you could look over here and this would be a guide. You'd be like, I'm not going to see it, not going to see it, not going to see it. I'm looking for OOCs. Maybe that's not a diffraction condition that actually applies to spinel. It may not, right? Every material has its own condition. Maybe it's like your A00 planes. Well, you could see them. You could say, okay, I expect to see one at 45 degrees, but these other ones, I do expect to see this one, maybe this one, but maybe not these ones. I use this tool all the time. That's up here in utilities. There are some other things like this one right here, standard orientation. Allows you to plot what's the normal way of representing this, right? Because you can look down any of these axes, but it also has this built-in standard one. meaning I don't know how they define that, but when people look at the structure, that's the most common way of showing it, which I think is pretty cool. Another thing they can do is under planes, I think it is. Where do they show you how to do crystals? A minute, let me find it. I have a YouTube video. I could always dig it up there. See if I can find it real quick. Crystal shape. Okay. So you can actually, if for example, you have like a truncated octahedral crystal, like when you're growing a crystal, maybe you know that it grows along the 110 faces, right? So you can do that. You can say like, let's have a crystal that grows along the 110 faces. You can actually generate these. So here it's actually, you can set the size. It's chosen a slightly larger size than we have, but then you could actually go through and you could delete out the atoms that are outside of this, or you could rotate it until you could sort of delete these. And if you wanted to, you could, after you delete those out, you could end up, I don't know, I'm being kind of sloppy here, but you could end up with a crystal structure that is in the exact shape that it's been grown. By the way, you can do truncated crystals, I'm pretty sure, with this. Pretty sure I've done that. Go back to crystal shape. Right now it's showing you the whole thing, but I believe that it can also truncate. Um, I'd have to remind myself how to do that. It's one of these options. But the point is that if you're trying to visualize a structure, Vesta can probably do what you want it to do. Let me look at a few options in the questions I'm seeing. Okay, so is it possible to add, oh, okay, so there are some problems. Somebody says, is it possible to, so first off, they said, how did you turn off the bonds again? I think we talked about that. And then somebody said, is it possible to add a legend? Unfortunately, no. That is such a bummer about this. And I hope that's something they'll fix in the future. That said, the way that I think you should do this, let me show up a good example of this. Annalise Mon, she does a good job of these. Article. Let's see if I can find one of her recent articles. All of hers look really great. There's a group of us that came out of Rom's research group and they do a good job. Yeah, so this is how she does it. I figured that she'd have one. First off, this was definitely made using Vesta. You can see this really nice, this is the table of contents graphic where she's trying to show something about ion mobility or something and defect tolerance. So this was definitely a raster output from Vesta where she's then added things over it. She's added these sort of explosions. I assume that those represent like missing atoms because she's talking about defects. And then she's added in Illustrator or something, this pathway for electrons, where in this material, it has no problem. It ignores the defects, but in this one, it doesn't. But why I bring this up is because look what she's done here to label this. Instead of having a legend generated by Vesta, she's actually mapped the color. CS, which those atoms are not shown here, are shown in green. The tin is this gray purple color, and then the dark purple is the iodine. Again, those are a little close and for me, like they're a little bit close together. But by changing the color of the atoms, that's a very common way to add labels. Here she's got cesium tellurium iodide, and the tellurium is now orange, and the tellurium is mapped with that same color. So it's a slick way to do legends on these. You can do the same thing with the axes. If you don't like the axes, by the way, just look how like all these figures in this paper, move this over so I can see it. These are all made in Vesta, and you can see what a great job. Here she's showing you the ABC stacking of this thing and how it's different for the two different materials. A nice job of showing the polyhedral connectivity. Just really clean, nice images, and all this made with free software, which is rad. By the way, check out, you've seen these before. We're going to show you how to make these diffraction plots in just a moment. That's our next thing we're going to do. That's Rietveld refinement. Again, you can, now she's made a composite image where she's done a multi-panel plot and she's added outputs from Vesta. She's zoomed in on just individual polyhedra in both skeleton mode and filled in mode, presumably to represent different things. Maybe this is like a vacancy surrounded by those. I don't know what's going on here. But it's a great way to take a complicated structure and the concept from crystal chemistry and represent it in a beautiful way. And it's really not very hard. It just takes a bit of practice. And she always does a great job. So I'm not surprised that this figure is no different. Okay. That's the question about legend. Somebody else says, I like the unusual planes or what it does. Thanks, I'll leave that. Somebody, okay. Well, spinels look amazing from what I had to learn in grad school. Yeah, I remember when like I said, when somebody explained spinels to me, they made no sense at all. It is so much clearer when you can actually pull up the structure. I don't see the data range below under conditions. I'll come back to that and then great utilities. So let's come back to data range and take a look at that. So the range tools, I'm going to turn off my crystal habit. So I'm going to go back to edit data and under crystal shape. I'm going to turn this, let's leave it on for, I'll show you. Maybe you want to keep it. And this might be one reason why you might want to keep it. Let's say you want to add atoms to fill up this crystal habit, right? That sort of polyoctahedral shape. So I'm going to go to boundaries, and you could just extend it, right? Let's say I want to go like -3 to +3. Let's try going, oops, I've done it. Put a negative in front of there. -3 to +3 in all directions. This should be more than enough atoms. Yeah, it is. So now if you wanted to delete out the atoms outside of this, first off, let's turn off our bonds because they're just making things messier. Or not our bonds, our vectors, like that magnetic moment. Let's just delete that out. So that's gonna make this a little cleaner. It's still pretty messy though. So one thing you could do is I find it's easy to look along the axes at first, and then you can start deleting out some atoms. Like I could highlight all of these guys and delete them as a start. There's a lot apparently because it's making my computer think. But anyways, I guess I want to do this whole exercise because it's going to take a minute. But the person was asking about data bounds. I hope that that answers it. And then you can delete this. If you accidentally deleted the wrong thing, you just hit escape and it brings all the deleted atoms back. As you delete these, it should get faster because it's rendering fewer because you're telling it don't show those. So then when you have to rotate this and mess with it, it should get faster and faster as you delete out atoms. But right now I do have quite a few atoms and I've got a few things running on my laptop. If you close other things like your Chrome browser, your Zoom application, it's going to go faster because it's competing for resources that your CPU is providing. Anyways, but you could go about this like, then you could look along the B axis and do the same thing, the C, then you could start looking along, probably custom rotations at some point where you want to get a flat surface on either vertical or horizontal, and then you could delete them out. Forgive the dizzying process to watch this. But you could do things like this to start to delete them out, just to show you one last way I would go about it. Yeah, anyways, that would be one option. I don't know if that's answering your question or not. Oh, the data range comment was in regards to the powder XRD. So the data range, I don't know if you can change that. Let's try it. Let's come over here and we'll go to utilities. First I need to I'm just gonna close this one because it's taking up too much memory. I think it's thinking. I have to give it a second. But I don't know if you can change the data range. Maybe you can. So let me close this one. I do not want to save it. Okay, come over here to utilities, powder diffraction pattern. Under calculation conditions, oh, it does. It does let you change the range. If you only want it out to 70, for example, and even with different step sizes, I think it allows you to modify it. You can do so. So now it should only go from 0 to 70. Yeah, it does. Only goes from 0 to 70. Pretty slick. So it is possible to modify. The conditions, I only see the source option. So I don't know, maybe you can clarify. Oh, yeah, it could have an older version. Although I just downloaded this one like 2 days ago, right before our workshop. I re-downloaded Vesta because they do update it pretty regularly. And I've never contacted them to ask for a feature, but I know that others that have, and they were fairly responsive. This has a bunch of other stuff, like it'll do like electron densities, like it'll show you instead of just with bonds. It has an ability to show you electron densities, although I've never used that. Fourier synthesis, just some really cool things that this can do. So worth playing with Vesta. We can look through a bunch of other structures, but I think maybe we should shift gears and then we can come back to it. But let's talk about how you would plot some of these structures. Like you clearly saw in Annalise's paper, how awesome some of her Rietveld refinements are. Like these are great, but those don't look anything like the output of our GSAS software. GSAS is great for what it is, but it doesn't do an amazing job of creating final images that are, what we're looking for. Whether that's like a preview, we could download this to see the full high resolution, but it's gonna look good. Let's do it real quick. Yeah, like this is a really nice image. What's great about this? There's a few things I would do differently, but there's a lot of things great about it. First off, she's plotting things in Q space. What is Q space? Q space is just 2 pi divided by your D spacing. Normally we plot things as 2 theta, but the problem with 2 theta is if you look at 2 theta diffraction, it's going to show you solutions to Bragg's law for a very specific radiation. So if I use copper, then in this crystal, this germanium crystal, like the 111 peak is exactly at 20, whatever that is, 7 degrees. But if I used something other than copper, that would now be in a different position, which means that if I'm trying to compare my results with somebody else's, or if I'm trying to, in the same paper, compare neutron diffraction with, say, lab diffraction, they're going to be at different positions, which means they won't line up. So I think I showed you this last time, my last paper I talked about, let me pull it up real quick, in this Cobalt 304 paper. In this one, we did both neutron diffraction and lab X-ray, and I think we also did synchrotron. And to compare all of those, by plotting it in Q space, the peaks line up where they're supposed to, because otherwise, with different wavelengths, they're not going to line up. I think there's another one I can show you. Yeah, here's another one where we're plotting them in Q space. I think I had one with diffraction though. Okay, right here. Here, this is neutron diffraction, totally different wavelength, but because we're plotting it in Q space, they line up correctly. So really, that is the best way to do it, and it's not that hard. It's a very simple. It's a one line of code in your Excel spreadsheet to take, Q equals 2 pi divided by your D spacing. Okay, but other things about these plots that I think are nice is you show the actual data points with a marker. I like either filled or unfilled markers so you can see how many data points there are. And then I show my fit over it because sometimes you're wondering like how good of a fit was it. Here you can actually see how it's actually fitting to the data. And then to make it extra clear, I actually show the difference curve. I think those should all be there. But to make it easy for you guys, I've put together a script that will actually plot these things. So if you go back to now the ceramic felt refinement GitHub repo, under the plotting example, I have 3 Python files that you guys could consider. The first one is a GSAS to XRD Rietveld plot, right? And when you run it, it will create figures that look just like you're seeing there in Annalise's paper and mine. So let's go through an example of using that. But before we can do it, well, I guess we can open it real quick. I'm going to open up the actual file. This is going to be opened it's a Python file, so you have to have some sort of Python installed on your computer in a Python environment. Those are all free. If you don't know how to do that, I can just walk you through it afterwards. It's pretty easy to do. But let's show you what it looks like. I'm going to use Visual Code Studio, but you could use Spider or PyCharm or whatever else. If you like Jupyter Notebooks, we can convert this to a Jupyter Notebook really easily. Not a big deal. Really quick, you tell it to trust myself. What's asking that? So if you haven't coded before, first off, there's never been a better time to dive into coding because now with things like ChatGPT, it has literally made this effortless. You can just tell it. Like if you don't know what any of this stuff is, not a big deal. It will do all the hard work for you. There's just a couple things that you have to do, and I've actually updated our steps to tell you what those are. Like if you went back, remember our felt refinement slides where I had the steps to do the different things, like here's, step by step what you do. I've added at the very bottom of this last night a step-by-step guide to using this Python file. Like it tells you how to export your data from GSAS, how to modify the code to make it work step by step. But let's show you it, okay? So let's say that we want to use this code. Well, one thing it's going to ask for is it's going to ask for the data, right? The output of your refinement needs to be saved to this refinement.comma separated values file. So before we do anything in this code, we need to get our data from GSAS. So we'll come back to the code in a second. Let's open up GSAS. Open up GSAS and close that and get it to output something. I'll show you how to do that. GSAS has a lot of cool export options. If you've run a refinement and you're satisfied with it, remember you're deciding to abandon it, it's good enough and that you're at the point where you're ready to abandon it, then there's a lot of cool options for exporting things, and we'll show you just a couple of them. Just a second to wake up. Okay, I'm going to open one of our files that we've been working on together. So I'm going to open, let's do the refinement where we did 90-10, this one right here. So in the file where it was 90% by weight alumina, 10% silicon, and we didn't get the refinement amazing, but we just abandoned it. We stopped for whatever reason. So if this was the case for you guys, you'd be in the same situation. You ran it and it got to we can run one more time and take a look. I think we got our R squared down to like 13% or something. And the biggest problem was that the two different phases had different shapes, and we just were sort of tired of messing with it. So you're ready to export it. Well, there's different options. In fact, there might be some options built in. I think there were, used to be anyways. Let me take a look. Hide that so I can see. Yeah, right here, there's save button is going to give you some options. Like you could save this right now as an image. So let's try it and see what that actually looks like. So in our folder where we were doing this work, I would go back to, excuse me, our refinement examples right here. And in the refinement folder, there should be now an image. So image.png, and there it is. And it's I don't know. It's not great. It's got the main information, but when I plot things, I like my font size to be the same everywhere, not like this giant label and this small one. This is all going to be small font compared to the font size of the text itself, which should be bigger. Maybe you didn't like the colors or whatever, and it was just too much of a hassle. Really, what you want to learn how to do is export the data and plot it easily yourself, especially using Python, because then you just run a code and it does it for you. So to do that, if you are done with this refinement, you can export it up here from the data tree window. You can do this export and you can export the project. If you export the project, it will just tell you the phases and the refinements, right? Let's just do like, this is the project. So let's come down to where that was and see what the project file was. So if I open that, it's by default a comma separated value folder file, excuse me. And this is it. It just tells you, okay, here's the phases, and it's giving you the lattice parameters of that phase plus their uncertainties. What's the phase fraction? What's the weight fraction? What's the size of that next one? What was its phase and weight fraction? And what was the refinement? So it's just like when you refine the phases, here's the information that I actually refined, and here's how good the refinement was. So it's like the bare minimum, most important stuff. But maybe what you want is not that. You actually want the data points for the fit and everything all compared with each other. In that case, you're going to export something different. You're not going to export the entire project. You're going to export the powder data. And by powder data, it's not just the powder data that you read in. It's going to import also the calculated pattern, the difference curve, all of that gets exported. What you want is this one. You want to export powder data as histogram CSV file. You don't have to write this down. This is all in this right here, right? Export histogram CSV file. This is all written down for you. So you can just sort of like watch if you want for right now. But if you export that, let's do it real quick. Powder data, histogram. We'll call this histogram. Okay. Here's what you're going to find when you open that file up. So histogram, it's a CSV, so you can open it in Excel or whatever tabular tool you want. It's got a bunch of columns, right? So at first, it gives you all the information like your instrument parameters, if you had a name for your X-ray diffractometer, what were the optics involved, like all this stuff. So we're going to ignore all of that when it comes to plotting because we don't show any of that information when we plot this. We're going to delete those rows out, and we're going to keep the rows starting with this X, Y, weight, calc, background, and Q, right? We're going to keep all of that. And if you wanted to, you could do this in Excel, right? You could plot right now in terms of Q space, you could plot it against the, the observed, the weight, all those things. You could plot those. So we could just do an insert plot and you could plot this data right here. And it's not plotting against Q. It's got those things wrong. What we really want is for this purple. You'd have to reset it. Excel's the worst. Like you wanted this Q column to be the X value, but whatever. I guess we could do this. You could go like this. And then you could plot it. Insert, plot, scatter plot. And there you go. Like it has all the data that you were interested in, but you're doing this in Excel, and Excel, there's just a better way to do it for sure. Okay, but once you've got this data, we can now technically run our GSAS to XRD plot. But what is missing here, if we go back to the types of plots that we want to create, like we look back at Annalise's, look at these cool tick marks. The tick marks are showing you where she expected to have a phase present. I think we had the same thing in my papers that I showed you. I guess I already closed it. But if you want to have that, then you have to show it where those phases were. And so we need one more bit of information. We need a column here that represents where did we see the HKL refractions for our phase 1 and phase 2. So we need a list of where those were, okay? So how do you get those? Cool thing is that this can also export those. So if you come up here and you go to export, you can export this HKLs. And this will do the same thing that we saw in Investa, where it did that simulated diffraction pattern, and it showed you the peaks, and it told you which HKLs they actually did. This does the same thing. We're going to export our HKLs. Let's just call this HKL list. Can we tell it to do it as a CSV? Let's try that. Because the default is not. Let's see what that does. Okay, we're looking for an HKL list. Let's see if that opens. Hopefully. So it did, but it didn't realize. Oh, I see. I told it was a comma separated value file, but there was no commas, and so it didn't parse it correctly. That's all right. We can just tell it to parse it. We can go to, how do you do this again? There's a way to do this. Here, let's just do this. Let's close it and let's re-export it, but we won't do it as a CSV this time. We'll just open it in Excel. So we're going to export this. We'll call it HKL underscore list, and we won't give it that extension. Then when we come over here, let's delete out the old one. Now we're going to open that file in Excel. Open. We'll browse to it. It's in this folder. Right now it's looking for Excel files, which this is not. So we're going to type all files, and there it is, HKL list. And all it's going to do, it's like, hey, I don't know how to open this. Do you want me to try it anyways? Yes. And it's going to say, here's the data. What do you want me to do with this? And by default, it's going to select what it thinks is the best way to parse it, which happens to be the correct way, using space separated values. And now you've got the data. And here you go. For your two different phases, like here's for the alumina phase, it's showing you all the HKL values and where the peak occurred. The only thing it doesn't do is show it in Q space. It shows it in 2 theta and it shows it in D spacing. It doesn't show it in Q. Well, no big deal. We can calculate Q. Q is just equal to 2 times pi divided by your D spacing. Easy peasy. So we'll take that. And there's our list of D spacing or Q spacings for both phases. Okay, so we're going to grab this list of where we expect peaks to occur, and we're going to slap it on right here. I'm going to paste values. Don't paste regular because it will just show, it'll paste the formulas. We want to paste values. Where's the values? Right there. And then do the same thing for our phase 2. We're going to grab this list of Q spacings, come over here and paste it. Okay, so now we're ready to go. We've got our histogram. Okay, now it's ready to send it to our Python to make a beautiful plot with no effort. So we can close this. We don't need it. We can come back to, let's close all these things down or minimize them. And guess we don't need GSAS anymore. We can close it up. Yep, close that. And now we go back to Visual Code Studio. Okay, now we technically have the file it needs to plot. This one was named refinement.csv, but ours is just named histogram. That's fine, we can rename it. So we say, we want you to open the histogram.csv file, and then you can just run this, right? So it's going to run it, and it's going to create an image. The final at the very end, it's going to name it. What's it going to name it? It's going to call the xrd.readfelt.png in the same directory where it's been working, which is where it read that thing out. So we should see right here, it just created this image, right? It was updated on August 1st at 10:08. That's right now. So it just updated that image, and here's what it looks like. So it did all the hard work for you. If you're not like a Python whiz, or if you don't know what a good figure looks like, or you don't know how to make it actually happen, this just did it all for you. Super, super simple. That said, when you generate your data, you might have to adjust, you will have to adjust a few things. For example, it didn't know what the intensity was. It didn't know what the range was. It didn't know what the phases were. So you do have to make slight updates to the code, but it's really simple. Like like 99% of this code, you just leave alone. And I've added a few notes for things you have to update. Like, what's the range? Does it go from 1 to 5, or does it go to something else? Okay, so update these values. You can change your own colors, or you can use the ones that I've got here for my postdoc advisor, which are beautiful. What was the final weighted residual? I had to update that to say 13. Maybe you got yours down to 5. Great, then you could change that to 5. Maybe your intensity actually went up to like 20,000, right? Maybe that was the highest intensity, and you actually want it to be in increments of 5,000, right? You can update those. Maybe you had different phases. You didn't have aluminum 203. Maybe you had like chromium 203 or whatever else, right? You could adjust all these things. Maybe the weight fraction here was like 10% and 90% instead of the 97 and 3 that we got. The point is that you could update all this. Maybe this, again, that's chromium oxide. Then you could rerun it. Hit the run button, give it like 1 second, and then you can reopen this, and everything's been updated, right? Now it's not better because in this case, it was already pretty good. But what's great about this is that it's showing you actual data points, the fit, the background, and the difference curve. All that information's there. You've got you're telling it what the weighted residual was and what the weight fraction of your phases was. And then up here, you've got these tick marks that show you where the different expected phases were. And you could change the colors of any of this if you want. But I just think that this makes it really, really slick. One thing is, what's great is you can copy this code and then you can jump over here to ChatGPT and you can modify it really easy. So you can go to ChatGPT and let's say that you're not like a coding expert and you're like, I don't know how to do this. Well, great. You come over here to ChatGPT and you can say like, here is a block of code. And then you can say, I want you to modify it. My max Y value was only 10,000 or maybe like 12,000. And my phase was AL203 instead of CR203. And anyway, let's just try with that one to start with and run it. And it'll say, okay, I can swap that. And it will make the adjustments to your code in real time for you, even if you're not a coder. And I'm using like ChatGPT 4.0, but even if you use the non-paid version of GPT, it's still really good. So let's see if it did it. Yeah, check it out. It adjusted this and it even adjusted the tick marks to a more reasonable value. I had it at 5,000, 20,000. It adjusted it to 12, and it even knew to use a smaller tick mark spacing, which is so cool. Here it replaced that to Illumina. It moved it back to Illumina, right? This one also got moved back to Illumina. So I don't know. If you guys haven't messed around with language models and coding, you're going to be absolutely leveled at how good it is. If you didn't like the colors, right? So you can say like, okay, great. Now I want the data points to be like, what color are they now? They're now that blue color, to be very purple, right? Right. And it will update the color for you in real time. In other words, you don't have to know anything about coding except how to copy and paste code into some sort of environment like this, and then hit the run button and see the output. And then you look at the output and you say like, I actually don't like that very much. Make this change. And you describe it just like you would describe your assistant, and it makes the change for you. So let's try this. Let's grab all of this and see what it's done. Sorry, not all of this. Grab just the code. Copy code, come over to Visual Basic, grab that, paste it, run it, see what it's done. Come back over here to our refelt. Did it get a chance to update? Or maybe because I had that open. Let's try that one more time. And over here, open up our file. It's not purple. Did I not copy it? Or did it not change it? Here it's actually setting the color manually. That was for the what? For the observations. If it doesn't work, you can just tell it, hey, it doesn't work, try it again, because something's wrong here. And it's typically pretty good. Anyways, that's how you can use the output of GSAS to create the data needed to generate these types of figures. Again, I think they're pretty awesome figures. You could just use it exactly as it is, or feel free to modify it and get it how you like it. But I think they're pretty great. For example, one thing, you're like, hey, this background's kind of cluttered and I can't really see the difference curve. Well, you can modify that. You could come back over here and you could say, go to ChatGPT, like, now for the, what's it named? Background curve is called the fit minus, oh, for the difference curve. Okay. You could say now for the difference curve, can you shift it down by 1,000 or so that it's easier to see, right? And let's see what it does. So you have to give it a moment for it to finish doing its thing. It should just add like a minus 1,000. So you could do that yourself, but if you didn't know how to do the coding, it can do this for you, and it will do it pretty, yeah, right there. It's just taking the fit minus the observed. This time it's going to minus it by 1,000. So it should show up more clearly on your overall figure. Give it a minute to finish. There it goes. Copy that code, drop it into Visual Code Studio. Oops. That's not what I wanted. There we go. Run it. I had to close that, sorry. Run that one more time, and that was closed. And why am I not seeing that shifted very much? That should be what's missing here. XRD refill, PNG. I'm in the right folder, right? Did it do minus 1,000? Yeah, minus 5,000. What's missing here? Something's up. It's 10:15. Did that file get updated? Ah, oh, is there an error that I'm missing? Because I've got this. Ah, okay, let's see. No, that should work. 10, oh no, let me delete this out and try one more time. Okay, there it is. Ah, okay, so I don't know what's going on there. Maybe I said delete that file out. But yeah, it's moved that thing 5,000 down, which is too much. It did change it purple. Let's go back and fix that really quickly. It's only 1,000. 5,000 was way too much. In fact, 500 is probably plenty. Run it one more time. Time after I delete that. See if that's working now. Okay, there it goes. Right. So you could feel free to adjust this as you want. You could say like, hey, the legend is overlapping, increase the Y maximum so it's not overlapping so much. And with language like that, it does a really good job of adjusting the code as you like. Okay. Let's take a look at some questions. Somebody says that's helpful code. I'm very comfortable with MATLAB, so I may write my own code for plotting, but I will try Python out. I really encourage it. I learned MATLAB in school, and I then didn't have it when I went to grad school because we didn't have a license. They used Mathematica instead. And all that coding, all that syntax I learned was for nothing. Python is free and openly available for anybody to use. I'll say that this at all universities, they have all abandoned MATLAB and they've moved towards Python. There's a few holdouts, but there's been a real shift in academia from MATLAB to Python, and industry is lagging a little bit, but I would highly recommend it, especially where I've provided the code for you and it's easy to use language models to do the syntax, but as you like. Um, okay, so we've got 13 minutes left. Let me show you some other cool plots that you might consider, just in general. For example, if we go back to Annalise's paper, you saw, first off, here's what we call a multi-panel plot. And this wasn't like four plots made individually and then like Frankenstein together. This was made all in one shot. So how do you make a plot that has four different panels like that? You cannot do that in Excel. Well, I've said that, and then somebody showed me you actually can, but it is not easy. It is a huge pain in the butt. And it's pretty easy to do in Python. So if we go back over to our ceramic repelt refinement, I've already showed you how to use this first Python file. That's gsas to xrd. And I've provided you the steps to follow. So if you missed what I was saying today, you can just follow it. Or I'm happy to show you via a one-on-one tutorial. But let's talk about this generic single plot. If you just want to make a regular plot, let's show you how to use that, because even if it's not diffraction data, just a basic generic plot is good to know how to make that looks nice. So if we go to our plotting examples, we open up our generic single plot. Let's go ahead and run this one and show you what it outputs. So it's going to create this in the same folder. I've actually added some generic single plot data, and it's going to create this generic single plot. It's going to do a really good job of making a figure like this. So what's great about this figure, this is all my opinion, but I like square figures because when you put papers in a two-column format, if they are landscape style, then it gets really small. Square just gives you more space to work with in a two-column format, which is where most of us publish. But feel free to adjust it as you like. You've got different markers for each phase, right? Different data set. You've got large and consistent text size all the way throughout. This is aimed to be such that the text size here will be the same as the text size in your paper, roughly. It shouldn't be much smaller or much bigger. It should be about the same size. And if you look at some of the papers that I've showed you from our own research, that's kind of what we aim for. If I look at like this cobalt paper, that's how it looks, right? So again, two-column format. You want this text to be kind of ish the same size as the text everywhere else. Here it's maybe a smidge bigger. I would err on the side of it being a bit bigger than too small. I've seen many, many figures where it is too small and you can't read it, right? So I think square figures do a good job of that. you want it to be easy to tell the two different data sets apart. Here I'm using two different colors, one broken line, one unbroken line. And when I'm plotting the derivatives, it's a different type of broken line, right? Here's another example of a two-panel plot, which I'm going to show you in just a second. But here's a single panel plot where we're trying to make it as easy as possible to read. I have a lot of opinions on what make for good figures. If you don't care about it, then that's fine, just skip it. But if you're somebody who's like wants to make better figures, I have a whole YouTube video on what I think makes good and bad figures. And I've included them in this ceramic refelt refinement GitHub page. If you scroll down to the bottom, it's got a link to that. So it has a link for a tutorial for Vesta, a link for our tutorial on GSAS, and the last one is a tutorial on making nice figures. So in 10 minutes left, let me show you how the multi-panel plots work before we run out of time. We've shown you now a single generic plot. Let's look at multi-panel plots using Python. So this time, if you run it, it's going to generate this. So it's going to pull from this data set that I've provided you, spectroscopy. And in this data set, if you open it up, it's got a bunch of different data sets. Like here's one data set, here's another data set, here's another. It's pulling from those, and it's going to create a multi-panel plot. So the multi-panel plot output looks like this, where maybe you wanted to have like one big tall figure over here, and then two small figures like that, or whatever. And then you have a common Y label, a common X label, and it's super clear. I'm using the Seaborn color palette, which is very pretty, nice colors. We're using different marker sizes. The text is all just sort of taken care of for you. And because this, again, is in the era of large language models, I can take this block of code, I can come over to ChatGPT and I can modify it. I can say like, let's do a new one. I gotta move this Zoom window. Hide that. Okay. I can say, hey, take this block of code that creates a multi-panel plot with one tall figure on the left and two small figs stacked on the right, and reverse it. I want the tall fig on the right hand side, right? Give it the code, tell it to do its thing. It'll take just a second, but it's definitely going to know how to do this. Or if you could have just as easily said, like, I actually need three block boxes on the right-hand side, or like I want a 2x2 grid instead of a 1x2 or whatever it was. You give it just a second. It's doing all the hard work of learning to use matplotlib, which is not like the most intuitive Python library, and it just does it for you, which is shocking how good this is. So it's made the changes. Let's try it out and see if it actually worked. I'm going to copy that code. I'm going to come over to here and I'm going to paste it and run it. And let's see if it actually did what we told it to. What was that? Multi-panel plot, and see what it did. And I don't think it did it. Let me try that one more time. 1021. Refelt refinement, plotting. Let's delete this out real quick and try that. Oh, it even named, it did it. It even changed the name. You clever Python, right? It even changed the name of the output plot to now reversed. Now it's got some issues, and you can tell it that. You can be like, okay, good, but now the y-axis is overlapping them. Fix it, and it will fix it. So in any case, I think this is pretty awesome that it can do this type of stuff. Let me undo this and go back. That was good. Okay, we've got just 5 minutes left, and I'm guessing there are questions. So let me turn it over to questions in the last 5 minutes, because I can always schedule one-on-one with people. But while I've got everyone here, are there general questions I can answer about refinement, about Vesta, about creating figures when you're done, about where resources are located and how to access them? Do you want to see more examples, just common crystal structures in ceramics? What would be helpful for the last 5 minutes of class? People feeling just overwhelmed. We covered a lot in just whatever it's been, 6 hours more.
I'm digesting it all.
Okay.
Yeah, I got my list, but I don't have, there was a lot to integrate, especially with all the the new language models in the Python. I won't do
Yeah, and
that.
if you are somebody who's never used Python, for example, I'm very happy to help you get up and running. Visual Code Studio is what I recommend using.
I'll start there. Yeah.
But if you want to use a Jupyter Notebook, which are also really popular, you could do that. In fact, like you can go to Google Colab and
Oh,
you could run it in the browser without downloading anything. Google
Ooh.
Colab, I'm pretty sure that I could just drop a file right into here and it will run in
oh,
Google Colab for free, which
whoa.
is pretty rad. So let's actually try it. They might only do notebooks. I don't know if it'll run a Python script. Let's try it. I don't know if this will work or not, but we can give it a shot. Let's take this code and let's see what happens.
Very
I don't know if
neat.
this will work or not. Because it's meant for running notebooks and we're running a Python file instead, a Python module, so it might error. Okay, yeah, so it errored not because it can't run the notebook, but because we didn't upload the file. So we would have to tell it, we'd have to upload the file with it because we're telling it to read data from a file, but we could do that. That would be a trivial change. You could take this exact same set of code, you could copy it, come over to ChatGPT and say, hey, I'm using Google Colab. How do I get it to read the file? You're gonna have to upload it to your drive is how you're gonna have to do it. But yeah, it would actually work there. So if you want to run it in just your browser without downloading Visual Code Studio, you can do that. I still recommend that you get Visual Code Studio because it has GitHub Copilot, which is like an integrated ChatGPT right in your coding environment. Like for example, like right, see that right there, that how it showed up in grayscale?
Yeah,
It's
yeah.
automatically reading my code and it's suggesting what the next thing I should type is. Like when I have that, that's exactly right. Like that line of code is meant to be setting the limits of the plot for data set one. And so I can just auto complete that. And then right here, it already knows that that's what I'm supposed to type. So it's automatically adding comments, but it can do more than add comments. It can actually add code itself. That's why it's worth getting Visual Code Studio.
All
It's
right.
free and it is wildly good.
So
But
I'll be back with you because I've got to do some of your tutorials to go with this.
okay.
It's very cool question about PXRD and
Uh-huh.
SCXRD, and somebody asking what to do on the
Oh, let me
chat.
take a look. Okay, let me look
And
in
that
the chat.
sounds, I want to know about that
Okay,
too.
so
Thank you,
I remember
everybody.
saying, in general, do we need PXRD for refinement or SCXRD? So the difference between PXRD, that's powder X-ray diffraction, and SCXRD is single crystal. When to use which one? So single crystal is always better than powder diffraction, always, always, always. But it's also way harder to grow and obtain a single crystal, and it's also harder to mount it, and the analysis is harder. So everything about single crystal is more challenging, but the output is way better. I would say if you think that you've made a new compound, like a new crystal structure, then you have to do single crystal. You can't do powder diffraction and report a new structure, or nobody's going to take it seriously because you can't accurately refine all the information that you care about. And it's oftentimes not ambiguous. Multiple different phases can generate almost the same powder diffraction pattern. And we have a good example of that with Heuslers, like half Heuslers, and superstructures of rock salt can all basically give the same powder diffraction pattern, but they will not give the same single crystal. So what I haven't covered in this week's lecture is single crystal diffraction. And I would have to I'd have to refer you to my colleagues who are better at it than I, because it's really not my area of expertise. Who I would recommend is Anton Oleynik at Hunter College in New York. Super nice guy, very, very good at single crystal diffraction, but there's many others. But I would say, again, if you're trying to identify and prove that you have a brand new phase that's never been discovered, like a new crystal structure, you really have to do single crystal. But for many, many other things, you can get away with powder diffraction. Somebody else says, I've used Google Colab all the time. It's free, it's effective. It also has an AI Copilot built into it. Super glad to hear it. Somebody says, any tips to do refinement when there is an amorphous phase? Oh, good question from Julia. So that one, we didn't cover it in great detail, but I'm happy to help you out. Where it comes from, if we go back to our refelt refinement slides, I've got a few slides kind of where we show it. Let me briefly come back to this. So if we jump ahead in our slides, when we talked about right there. So if you see a big amorphous bump like this, you have two options. First off, you can just try and, well, I guess you have three options. You can try and fit that amorphous bump with a more complicated background function. For example, we're using the Chebyshev polynomial with just three terms. You could crank up the terms and just try and fit it, right? That's one option. Second option is just cut that part off. When you do your refinement, add an excluded region all the way up until like 25 degrees on this one. I would just be ignoring this one. Or the third option is, what if you actually want to quantify the amount of the amorphous phase present? Then you have to actually rerun your powder pattern with an added standard calibration. So we have an example of this in the notes provided, right? So if you go back to your refinement examples, there was this folder right here, which we didn't do. That's Al2O3 plus silicon plus silica. In that example, what I did is I took the exact same powder that we had before, which was 90-10 alumina and 10% silicon. But this time I intentionally ground up a known amount of silica glass, which is going to be an amorphous phase. And you can do the refinement on that one. In that scenario, you know exactly how much standard there was. In this case, we know that there was 10 weight% silicon. And so you can redo the refinement, and the weight fraction that comes out of the refinement will be different because now you have a new background that was present. And you can use a ratio because you knew how much silicon was there. You can use a ratio to figure out how much amorphous content must have been added. And the way that you do that is by simply using this SMZ method. The SMZ method tells you the SMZ for each individual phase divided by the sum of the SMZ phases. And all we're doing is we're adding one more term in the denominator that represents our amorphous phase such that we get the observed X-ray diffraction. In other words, you know what the value should be, but you see what the value is being output from your diffraction, and therefore you can calculate the amount of your amorphous phase. So to do this, if you ever want to refine the amount of your amorphous phase, to do that, you have to go back and you have to rerun your X-ray diffraction pattern with a known amount of some calibrated standard. Very oftenly, you're going to use silicon because it only has a few peaks, so it's not going to bugger it up with a bunch of extra messy peaks. But you could use anything you want. You just have to know exactly how much by weight fraction you added. And then all you do is you add an additional term in this calculation and you do it by hand. GSAS is not able to output this for you. You're going to have to do it by hand. But it's not very hard. It's just a ratio. Somebody else says, if I have a highly asymmetric peak, long tail on the low 2 theta side, and they've included a picture of it, that is a really bad one. Are the instrument shape parameters best for fitting? Yeah, but you're going to have to turn on that SH/L parameter. So if we go back to our, really quickly, geez, I had so many windows open. Let's open up GSAS one more time and just show you it one more time. But that SH/L should be able to account for this. Really, though, what you should do is you should probably go back and rerun your sample. If you want to get rid of that really bad asymmetry, what you want to use are Solar slits. If you guys aren't familiar with Solar slits, move that out of the way so I can see it. Solar slits are a series of converging. Converging. They take a diverging beam like this, and it's a bunch of literal like mechanical plates that are very close together that are parallel with one another. And so it takes a diverging beam and makes it a converging beam. Now there's always a trade-off. Every time that you improve the optics of your X-ray system by, for example, using tighter slits or Solar slits, what you pay for is intensity. A bunch of the beams that were diverging get absorbed and they don't go through. Therefore, your intensity has gone down. So your overall signal to noise ratio just got worse by using Solar slits. But in your example, where I'm seeing that those asymmetries are so intense, it would be worth going back and rerunning your experiment, if that's still an option, and using some tighter Solar slits, because that will annihilate this asymmetry problem. If you don't have that option, then what you have to do is you would open up your GSAS, like let's go to one of our files that we've been working on. Whatever this one is fine. And under your instrument parameters, there was that SHL. So I'm going to go to instrument parameters. This one right here, this SH/L, that's your anharmonious. It's basically your asymmetry parameter. You're going to want to definitely turn that one on, but it's going to be harder to fit. Like for sure, looking at that figure that you've posted here, that's going to be a harder refinement to fit because that's a really wonky shape. In fact, I'm not even totally sure if it, let me click that image and make it bigger. It might actually be, yeah, no, that is asymmetry. I was going to say it might be a secondary phase that's just to the left of it, but no, that's it. It's just really asymmetric. But yeah, turn on that SHL and see if that can fix it for you. And if it doesn't, rerun it with some solar slits to clean up the peak shape a little bit. Somebody says, how can I become better at refining? Okay, practice. You just need to practice and then talk to people about what you've done. So afterwards, arrange a Zoom call with me and be like, hey, can I walk through the steps I took? Are any of these like silly steps that I shouldn't have taken, or an unphysical refinement, which is, while it's giving me a better fit, it's doing so at the expense of something that is realistic and possible. But practice, you just have to practice. It comes with time. I've done this for 20 years now. So my first many refinements were pretty trashy, but you only learn by trying. And then second question, is it possible that some of the parameters for fitting may help in lowering the RW? Yeah, exactly. But may not be actually useful for the refinement. 100%. You could turn on all sorts of stuff that will put the curve fit closer to the data points, but it might do so at the expense of actual knowledge generation. You want in the refinement to generate knowledge and understanding. You want to learn something about your system that you didn't know, like occupancies or thermal displacement parameters or whatever else, right? We saw the example where sometimes it might give you a better refinement fit, but the thermal displacement parameters turned into completely crazy numbers. You can get the same thing where it might move atoms, so now they're overlapping each other, or the lattice parameters are so big that your bond distances are totally incredulous, and yet it might have given you a better fit for whatever reason. So you should be a skeptic, like all models. Like I tell my students, we do a lot of machine learning in my group, and I always tell my students, models are all wrong, but some are kind of useful. So your job is to figure out in what way is it being actually useful, or is it just being wrong, right? And you should be skeptical of everything you're doing and prove to yourself, not prove to others, that you're making the right choices. Other questions? We're kind of a little bit over time, but I'm happy to keep answering them if people have questions. Okay, if not, please be, I'm going to put my email here one more time in case you hadn't gotten it, sparks@eng.utah.edu. I am an easy person to find. Just reach out and I would be happy to do one-on-one sessions to explain things if we didn't cover it. Or honestly, when you try this out, you're going to have more questions anyways. So whether it's plotting in Python, using Vesta, general ceramics questions, I'm happy to be assistance.